Hello, welcome to my channel. Today we are going to discuss about inverting summing amplifier, where I will give you a small description about the circuit, show you the circuit diagram, derive the final equation, and solve 3 practical examples and simulate these examples on a simulation software to verify the results. So where do we use such circuits? If we have multiple audio signals from different audio sources and we want to combine them together to form a single output voltage, or if you have multiple signals from different sensors throughout the system and you want to combine them together to form a single output voltage, we use this op-amp circuit called summing amplifier. The input signal can be of any form, whether it's DC or a waveform. If it's DC, it can have any value. If it's a waveform, it can be of any size or shape or can have any frequency. We can add them together. So in practical scenario, these two signals might come from a different mics or audio sources, and this signal might come from a sensor, and we add them together. We have each channel for the signals. This might not be that simple, but this is the go-to-go theoretical approach. The most important thing that we need to consider is that it's not a simple summation of the input voltages. That means if we have 1, 2, 3 volts as the input, the output is not 6 volts. Rather, it's a weighted sum of the input signals. That means the output voltage is not just V1 plus V2 plus V3, because we are not dealing with a summation circuit, rather it's an amplifier. Amplifier comes from the word amplification. Amplification means scaling up. For amplifier, there is a special parameter that we need to consider, that is gain. So we take each input values and we multiply it by the gain. We get those values, then we add them together. That means this is not the correct form of the circuit. Rather, the output voltage will be V1 multiplied by the gain plus V2 will be multiplied by another gain, and V3 will be multiplied by another gain, and the entire summation will be at the output voltage, and such gain will depend on the resistors that we are connecting. If you don't want to go through complicated derivation, you can find the output voltage equation pretty easily using the theoretical knowledge. As I said earlier, if you take the input voltage and multiply it by the gain and you add them together, you will get the output voltage. We have the input voltages V1, V2, V3 will be given, and if you connect the sources, we will know the input voltages, but what we don't know is the gain, A1, A2 and A3. So how do you find the gain? If you look at the circuit or consider each individual channel, the circuit looks like an inverting amplifier. The inverting amplifier equation is minus RF by the input resistance multiplied by the input voltage. This is the very first equation you will learn in the OpAmp chapter. V1 is the input voltage which we have. RF by R1 is our A1. So we have our gain, we have our input voltage. Repeat the same process for other channels as well. That means minus RF by R2 into V2. We are just using the inverting amplifier equation for each channel. Again, minus RF by R3 into V3. This portion is A2, this portion is A3. We add these three together and we will get the output voltage. That means output voltage is equals to minus RF by R1 into V1 minus, plus minus is minus, minus RF by R2 into V2 minus RF by R3 into V3. You take RF as common, RF this is our output voltage for the summing amplifier, inverting summing amplifier circuit. To be honest, you don't even have to memorize the equation. All you have to do is apply the inverting amplifier equation for each channel and just add them together. Now we will derive the final output voltage equation for this circuit using KCL and Ohm's law. Before that, we need to consider two important assumptions of OpAmp. That is, no current can flow into the terminal. for both the inverting and the non-inverting. That means the current in this path is always 0. The second important assumption is that the voltage in this node is equal to the voltage in this node, and the voltage in this node is 0 because the non-inverting is connected to the ground. Therefore the voltage in this node is also 0. Now this path is clear. We can say that the current through each channel flows and combines in this node. They flow through this path and end up on this path. So we can say I1, I2, I3 gets combined and flow through IF because no current is flowing through this path. So if we implement KCL, I1 plus I2 plus I3 is equals to IF. If we apply Ohm's law is V is equals to IR, I is equals to V by R. Voltage is the voltage difference between the resistor. The conventional sign for resistor is plus and minus. We take the voltage on the plus side minus the voltage on the negative side. The voltage on the plus side is V1. V1. The negative side is the voltage is 0 because we, according to the second assumption, the voltage at this node is 0. Therefore V1 minus 0 divided by the resistance is R1 plus, we repeat the same for each channel. The voltage on the plus side is 0. The voltage on the negative side is V0 divided by RF. Now if we simplify, if you take RF to the other side, this is our final voltage equation.